Let me see if it here it's good. Nope. I think here is the best. Pardon me?
Because that part is not.
That part is not clear. No, wait. Now it's clear. Yeah, but okay. So I'll try to do my best. I don't know where my original camera is, but sorry about that. Great. So last time we were discussing the group, well, the set of equivalence classes, Z modulo and Z. Z modulo Z. It's the set of all equivalence classes modulo n. We saw that we can define an addition on Z mod NZ, right? We can define an addition and a multiplication on Z modulo NZ. Okay? So we can define an addition, and these are well-defined operations. Addition plus, so how do you define this? The class of xn plus yn is equal to the class of x plus yn, and multiplication, operation I'll be calling times. It's the class of x times the class of y is equal to the class of xy modulo n, and these are well-defined operations, right? Great. Now, Z modulo nz, the first thing to do is that Z modulo nz is a group under addition. Z mod nz plus is a group. Why is that? Well, first, do I have a neutral element for addition? Yes or no? There is a neutral element for addition. X n plus 0 n is equal to x plus 0 mod n, which is equal to x mod n. So the class of 0 is the neutral element for addition, right? Great. Now, what else do I have to check? That's for all x and z, right? Right, for all x and z means as x regions in z, this equivalence class will be ranging in the whole set Z mod nz, right? Now, what is the equivalence class plus the equivalence class of minus x modulo n? What is that? Right? The class of minus x. I mean, the class of minus x, you can also see that as the class of n minus x, right? Because modulo n, they're the same. So I do have an additive inverse for every element of these equivalence classes. For example, mod 5, what would be the additive inverse of 1? Mod 5, the additive inverse of 1 would be?
4.
Additive inverse of 1?
4.
4, exactly. Mod 7, what's the additive inverse of 3?
4.
4. Mod 11, what's the additive inverse of 7?
4.
4.
No, it doesn't have to be 4.
No, it doesn't have to be 4, yeah.
Keep saying something that has 4.
I don't know, it's easier for, I don't know. What is the, so what are the numbers I use? I mean, I try to use like always 1 or prime numbers, I think. But anyways, 7 and 11. What's the additive inverse of, I don't know, 5 modulo 10?
5.
5, very good. Okay, great. So, and then we do have the associativity, right? Is equal to now those are integers in z for all x, y, z in z. So x plus y plus z which is equal to x plus y modulo n plus z modulo n. Okay, so this is a group. Yes, sir.
So about the well-defined function string, so we can't say that x plus y n is equal to x plus y plus n.
I don't understand.
When you say that the functions have to be well-defined, does that mean that we can't say that x plus y, the class of x plus y is the same as the class of x plus y plus n?
Yeah, exactly. Yeah. Whatever. So, for example, if you add 1 mod 5 and 4 mod 5, what do you get? 0, right? Now give me a number that is congruent to 1 mod 5. 6. Give me a number that is congruent to 4 mod 5. 9. 6 plus 9 will also give you 0. So whatever x you choose, as long as they're in the same equivalence class, the answer will be this.
But for the function, for it to be a function, you can't say that you can say they're congruent, but you can't say they're equal.
No, so what is a well-defined function from z mod nz to another set A? You need that if x is congruent to y, mod n, you need f of x, f of the class of x, to be equal to f of the class of y. Basically, your answer should not depend on the number representing the equivalence class, right? So if you have a function like, I mean, on the assignment, I think I give you a function to check z mod nz to z, and if you take the GCD of the class, well, of x and y, of x and n, sorry, you can see that this is a well-defined function. Okay? Great. Okay. Now let's see. This is a group. Awesome. Now, is z mod and z under multiplication a group? On the equivalence classes modulo n, I have a multiplication. Is it a group under multiplication?
No, because
Because of?
0.
Very good. So 0, if I were to multiply, I know that the equivalence class of 1 would be the identity element, right? X times 1 would be equal to the class of x. X times 1 is congruent to x. But, as your friend suggested, 0 doesn't have an inverse. 0 times anything is 0. You never get 1. Great. I mean, let's try to remove 0. If we remove 0, do we get everything? Let's see. I mean, what is the main issue here? The main issue will be finding inverses. I have an identity, 1, right? X times 1 is equal to x. So the class of x times the class of 1 is equal to the class of x. That's not an issue. Now, is the associativity an issue? So let's see. What is the class of x, y, z mod n? Let's take, sorry, where is what? The class of x times the class of yz is equal to the class of x times the class of yz. Now, since x, y, and z are integers, I know that multiplication of integers is associative. And hence this multiplication is associative. Right? Yes or no? Everybody. If x, y, z are integers. This is true, no? Okay. So I have an identity element for multiplication. I have associativity. What is the only thing left that I need? What is an important thing that is left that I need?
Well,
Yes,
isn't
sir?
it not closed anymore? Because like 0 isn't included. So like 2 times 2 under 4 is 0, which is not included.
Exactly. Well, that's a very good point. But that's a very, very, very good point. We'll see that. Now, I have z mod n z. I have the operation of multiplication. I have the associativity. What is left to check?
Inverse.
Inverses. Okay. Now, when do I have an inverse in Z mod NZ on the multiplication? And if I find the element that allow me to, if I find the elements that have an inverse, could I actually construct a group? Do I get a closed structure? Let's try.
Because if n is the square of some number, the number inside is multiplied by some 0.
Exactly. So these numbers should be removed, right? What numbers could I remove from Z mod NZ
The equivalent
to get
of 0.
a group under multiplication? So this is a proposition. Let A be in Z. Then the equation AX is congruent to 1 modulo N if has a solution if and only if GCD AN let's prove the theorem. Let's prove that proposition. Should I do it in one step or in 2 steps? What do you prefer?
One.
Let's try to do it in one. I mean, okay. Let's do it in 2 steps. I mean, you can do it in 1 step, but this way. So let's do this. Let x0 be such that ax0 is congruent to 1 mod n. Then, by definition, there exists k in z such that ax0 is equal to 1 plus kn, which means that ax0 minus kn is equal to 1. That's it. Okay, now, what can I say then? Yes?
But then you can say that the GCD of A and N is 1 because it's the minimum linear combination that you can get.
GCD n, very good, thank you, divides ax0 minus kn, which is equal to 1, and GCD an. Okay? One way is proved. Now I have to prove the other way. Which really means, which almost the same, you can just go backwards. Suppose that the GCD AN is equal to 1. Then there exists U, V, and Z such that what? AU plus VV is AU plus VN is equal to 1. Now, if AU plus VN is equal to 1, now take both sides modulo n. You can take both sides modulo n. What do you get? You get that AU is congruent to 1 modulo n. Hence, the equation AX is congruent to 1 mod n as a solution. Okay, that tells me which elements in Z mod NZ have an inverse modulo n. These are exactly the classes of the elements that are co-prime to n. Again, I said something that should force you to think of it. The classes of the elements that are co-prime to n. what does it mean that a class is co-prime to n? Okay, let's try to see that. Okay, let's give an example. Mod 5, for example, 3 is 3 co-prime to 5?
Yes.
So what's the inverse of 3 mod 5? 3 times 2 is congruent to 1 mod 5. Is 7 co-prime to 9?
Yes.
What's the inverse of 7 mod 9?
It's 4.
It's
4?
7 times 4
No, it's not.
is equal to 28, which is equal to 9 times 3 plus 1, which is congruent to 1. Okay? Very good. Awesome. Now, I claim the following. Let UN be the following set. It's the possible classes of residue modulo n such that GCD AN is equal to 1. I claim that UN under multiplication is a group. So for example, U5 would be all the elements that are the classes of all the elements that are co-prime to 5. 1, 2, 3, 4. Okay, from now on I will just write these. Okay? I will just write these. I will just write bars instead of brackets. Okay? Just a notation to facilitate a bit. And maybe later on I will just drop the ones if the context is clear. Okay? Now what is U8? It's the classes of all the elements that are co-prime to 8. Is 1 in there? 2. 3. 3 is there. 4.
No.
5.
Yes.
6.
No.
And 7. Okay? Should we give one more example? Should we give one more example? What's U11? Well, U11 is a bit big. Well, let's say 12. What is U12? What are all the elements before the classes of all the elements modulo 12 that are co-prime to 12?
1,
1,
5,
1,
Seven.
5, 7,
11.
8. Should we do one more or that's good? It's okay? It's okay? Great. Now I claim that UN under multiplication is a group. It's a group. The first thing to note is that this GCD business here is well defined. Let's try an example. Let's see. Okay, what's the GCD of 9 and 5? 1. And what's the GCD of 4 and 5? It's also 1, right? 9 and 4 are congruent mod 5. And when you take the GCD of 9 and 5 and you take the GCD of 4 and 5, you get the same number. Okay, this is a question in your assignment to show that this is well defined. That exactly. I mean, I think you have to show that if A is equal to B mod n, then GCD AN is equal to GCD B. Okay. It's not very. I mean, you might need to think about that a bit. But it's not very. It's not. It should not take you a long time. It should be a few lines, but the way of doing it is you might need some time to find the way of doing it. Okay, great. So UN is a group. Now I first need to check something. Your friend suggested that Is this actually closed under multiplication? If I multiply two numbers that I co-prime, do I get a number that is co-prime? So what is 3 times 4? 3 times 4, what is that? 12. Mod 5? 2. 3 times 5, what is that? 16. Mod 8 is 1. Okay, so
No, that's 15.
sorry,
So mod 8 is 7.
oh man, 50, it's minus 1. Thank you.
416 doesn't-
Minus 1, yes. 15 would be minus 1, which is 7. 5 times 7, what is that? 35. Mod 12 is
11.
minus 1, which is 11. Okay. First, note. If GCD AN is 1 and GCD BN is 1, then by homework 2, right, we prove that GCD AB and N is 1. Remember this exercise we proved in the homework? Yeah? If GCD AN is 1 and GCD BN is 1, then GCD ABN is 1. Hence, AB will belong to you. Okay? Great. So the closure, I get a closed set. When you multiply two numbers in UN, you get back a number in UN, a class in UN. So we're going to be more precise. This is I think one of the most important, it's the most, well, I don't want to say the most important, but an important fact that is closed. If you take the product of two invertible elements, you get an invertible element. Great. Hence, UN is a group under multiplication model. Do you want me to prove it, or I can leave it as an exercise? I mean, it's a. I think I've done all the steps. You just have to put them together. Is that okay, or should I do it? Should I do it?
You can explain it in words and then you can explain
I'll just do it. So let X be in Z. I need an identity element for multiplication. It's the class of 1. It's just X times 1, which is X. So let X be in Z. What I need is that let X be, well, for any Z, this holds for any equivalence class, so you don't really need the fact that X is in UN. It holds in particular for X in UN, so let X be in Z be such that GCD Xn is equal to 1. Then there exists U0 such that by the theorem we approved, AU0 is congruent, XU0 sorry, is congruent to 1 mod n. So the class of X mod n times the class of U0 mod n is equal to the class of 1 mod n. So I do have an inverse for every element in UN. Now the multiplication is clearly associative. I mean, I think I've proved it. That's all. I've shown how to get there. So let's take any class Xn times Yzn is equal to X Yzn, which is equal to Xy Zn, which is equal to Xy n. Okay? Yeah? So far so good. Is it a bit fast, or am I going fast, or it's okay, I think, right? Yeah.
We write faster than I write, but that doesn't mean too fast.
Yeah, but oh yeah, I mean on the board it's used to it now. Starting a bit fast. But are we good here? Great. Let's give some small calculations. I mean, do you want to do some small calculations on, let's give a number, let's say U5. I have 1, 2, 3, 4 with addition, with multiplication modulo 5. I mean, let's take the product of some element. 2 times 3, what is 2 times 3? Is equal to 1, right? We'll just be working with these classes. 2 times 4 is 8, which is equal to 8 is equal to 8, what 5? 3. Right? 4 times 3 is equal to 12, which is equal to 4 times 3 is equal to 12, which is equal to 2. Okay? Is that clear? Yeah, should be clear. Great. Now let's move on to more interesting stuff. Well, I mean, this stuff is interesting. And Zn or Un, are they abelian groups or not? Does the addition commute? Is addition commutative on Zn?
No.
Is x plus y equal to y plus x?
Yeah.
Is x times y equal to y times x? So Zn and Un are abelian groups. Is Un a subgroup of Zn? Is Un a subgroup of Zn or not?
Yeah.
Yes.
Un is not a subgroup of Zn. Un is a subset of Zn, but for it to be a subgroup, you need the same operation. Okay? So please pay attention. Un is not a subgroup of Zn.
What is it then?
It's a subset.
Why is it not a subgroup?
Because Zn has the subgroup definition, you must have the same operation.
Yes.
Zn and Un don't have the same operation. Zn is a group under addition, Un is a group under multiplication. These are not subgroups. Okay? Great. Now let's move on to a kind of new thing. Essentially, subgroups. Well, I mean, let's order of an element. Let's try the definition of order of an element. Let G be a group. And G belongs to G. The order of G is the minimum strictly positive integer, and well, strictly positive integer, I'm emphasizing it. In N, such that G to the N is equal to EG, where G to the N is just G, G, and G, like the operation of the group, n times. Okay? So let's take an example. Let's use a group under multiplication. For example, -1 in R minus 0 under multiplication. How many times you need to times -1 by itself to get 1, to get the identity element?
Once.
Is -1 1? Is -1 equal to 1? No. Is -1 equal to 1 in R? Is this n equal 1? So
No.
is -1 equal to 1? No. Is -1 squared equal to 1?
Yes.
Yes. As ordered. -1 is different than 1, but -1 squared is equal to 1. Let's pick an element in, let's see, GL2R, let's say, -1, 1, 0, in GL2R. What is the identity element of GL2R? GL2R is the group of 2 by 2 invertible matrices under multiplication. This has order 2, right? Has order 2. Square it, you get 1, you get the identity. Right? You're squaring a diagonal matrix, so like if you square a diagonal matrix, you just have to square the elements. So the square of that is the identity, and this is not the identity, so this has order 2. Now let's pick another interesting example. Let's see. 2 in U5. What is the order of 2 in U5? Two to the 1 is equal to 2. Is it equal to the identity? No. 2 squared, what is it equal to?
-1.
Minus 1, which is 4. Is it equal to the identity?
No.
No. 2 cubed, what is that equal to? 4 times 2, which is 8. Mod 5 is 3. 2 to the 4, what is it equal to? 16, which is 1. Or it's 3 times 2. You know, you go to the previous one, you time it by 2, you get 1. So what is the order of 2 in U5? Sorry, with Gn, if n is finite here. Apologies. If, I have to add, if such n exists. I didn't write that. If it exists. Apologies for that, I forgot. If it exists. Okay? Are we good here? Is it clear? You just keep taking the powers of the yes, sir.
I don't know if it was mentioned, what is order 2?
Order 2. What is the definition of order? It's the order of G is the minimal element
Okay.
and the minimal power, the minimal strictly positive power, if it exists, that gives you the identity. Okay? Now if I take a group under addition, this circle becomes plus, right? So it would be really taking n times the plus operation, right?
Which is multiple.
So what is the order of 1 in Z mod 5Z? How many times you need to add 1 to itself to get 0? 1. If you add 1 to itself once, you get 1. 1 plus 1, what is that? 2. Is it 0?
No.
1 plus 1 plus 1, is it 3?
Yeah.
Is it 0?
No.
No. 1 plus 1 plus 1 plus 1, is it 0?
No.
1 plus 1 plus 1 plus 1 plus 1,
Yes.
is it 0? So this 1 in Z mod 5Z has order. Okay, let's pick another element. You're in a group where the operation is multiplicative, let's say, or composition. Order of 1, 2, 3, 4, of 1, 2, 3, let's say, in S3. What's the possible? Well, 1, 2, 3 is different than the identity, so it doesn't have order 1. Has order, let's see, has order. Order of 1, 2, 3 in S3. We'll fill this in. 1, 2, 3 is different than the identity. Now 1, 2, 3 times 1, 2, 3, what is that? So 1 goes to 2 and 2 goes to 3, so 1 goes to 3, 3 goes to 1 and 1 goes to 2, so it's 1, 3, 2. Right? Now what's 1, 2, 3 cubed? This is just 1, 2, 3, 1, 2, 3 times 1, 2, 3. 1, 2, 3 times 1, 2, 3 is 1, 3, 2. Times 1, 2, 3. 1 goes to 2 and 2 goes to 1. So 1 goes to 1. Right? 2 goes to 3. Let me write this. 1 goes to 1. 2 goes to 3 and 3 goes to 2. So 2 goes to 2. 3 goes to 1 and 1 goes to 3. So this is the identity. What is the order of 1, 2, 3 in S3?
3.
3. Great. In general, I will give this here. Could I erase upstairs? Oh man, okay, you guys might have not written this. I'll erase this. In general, a cycle, a bijection on Sn. We call a bijection A1 up to AK in Sn has order K. Okay? You can prove that. So 1, 2, 3, 4. What's the order of 1, 2, 3, 4? Has order 4. 3, 2, 1 has order 3. Okay? 1, 2 has order 4. Okay? So what's 1, 2 times 1, 2? You can try that. It is 1, 1, 2. 1 goes to 2 and 2 goes to 1. So 1 goes to 1. 2 goes to 1 and 1 goes to 2. So this is the identity. Okay? Great. What's the only element of order 1 in the group?
It's the identity.
The identity, right? Take the identity to the power 1 is the identity. Conversely, if you have any element that has order 1, then it must be the identity. Are we good here, guys? Yes, sir.
Could you re-explain the order of the equivalent class in Z?
In Z mod 5Z? Here? Okay, so here the group is addition, right? That circle we have, that group operation is plus. So how many times you need to have 1 to add 1 to itself to get 0? 5 times. That's the minimal number of elements. Okay, great. Let's prove some properties about the order. Good question is, let G be a group, and suppose that G and G and let G and G have order n, let's say, okay? Then the following goes. If G to the K is equal to the identity, then n will divide K. Okay, so say you have an element of order 3. It is obvious that if you take that element of order 3 squared, you get G to the 6, you get back the identity, right? So say you have G cubed is equal to the identity, then G, any multiple of 3 here, you will just get back the identity, right? Just raise both to the power K, right? You get back the identity. Now, the converse holds. If you have G to some power is equal to the identity, then that power is divisible by the order, by the smallest number, by the smallest strictly positive integer, such that G to the n is equal to 1, and to the order of, let's say, G to the m is I think I forgot the formula. Let's hope this is good. Is n over GCD. Yeah, I think that's good. Okay. Let's prove these two facts. Let K be in Z be such that G to the K is equal to G. Right? K has Qn plus R, where Q is in Z, and R strictly less than n, and R and Z, right? R is an integer. That is strictly between 0 and n. Raise both sides to the power k. G to the k is G Q n plus R. Then, what do you get here? This is G to the n, G to the R, and G to the k. Agree? Yeah? Everybody agrees? I just played with powers the usual way. What is G to the k? Is the identity. What is G to the n? N is the order of G, so G to the n is equal to what? If n is the order of G, then G to the n is the identity. The identity to the power Q, what is that? Identity, 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 Q times, what do you get?
Identity.
Identity. I mean, you know, or if Q is negative, you can argue the same way. G to the R. Well, e.g., identity is equal to identity times G to the R. So G to the R is identity. Now, if R is strictly less than N, and G to the R is equal to the identity, what must be R? R is between 0 and N, 0 included and excluded, and G to the R is 0. And N is the minimal number for which you get G to the N is 1. What is G to the R?
0.
What is R, sorry?
R is 0.
R is 0, hence R is 0. So N will divide. Right? R is 0, so K is equal to Qn, so N will divide. Great! Now, let's prove the other. The order of G to the M. Okay. Let's prove 2. So that the order of G to the M is N over GCD M. Now this should be, first of all, the order of G to the M divides N over GCD Mn. Why is that? Just let me take G to the M to the power N over GCD Mn. What do you get? Well, you get this is G to the Nm over GCD Mn, right? Now, if you want, we can use the assignment 2 again. We don't have to, but let's do that. So it's GCD of LCM Mn. So really, it's G to the power a multiple of N, right? You know, let me erase this actually. It's not necessary. So this is G to the N to the power M over GCD Mn. Note that M over GCD Mn is an integer, right? M over GCD Mn is an integer because GCD Mn divides N. Belongs to N. Right? So you get it's equal to the identity of G, the power M divided by GCD Mn, which is equal to the identity of G. Okay, great. Now, I need to show that the order of GTM is exactly that one. Right? I have shown that the order of GTM divides this. Now I need to show that this is exactly the order. So let, to facilitate this, the order of G to the M. Hence, G to the M to the power K is equal to the identity. Agree or not? If k is the order of g to the m, then g to the m to the power k is equal to the identity. Can I erase here? Can I erase here? Yeah. Then g to the mk as order. Oh, sorry. G to the mk. Sorry, g to the mk is equal to the identity. Now, what do I know from the first proposition? Then, by part 1, if I have g to some power is equal to the identity, then that power will be divisible by the order of g. Hence, the order of g divides what? Divides mk. So n divides mk. Okay? So n divides mk. What does it mean? If n divides mk, does m divide mk or not? N divides mk, and m divides mk. So mk is a common multiple of m and n. Hence, by homework 2, mk is a multiple of n. Sorry, I just have to take this phone and I'll be urgent. Okay. Yeah, sorry about that. Then mk is a multiple of n. Then mk is a multiple of LCM mn, right? Which is equal to, what did I say? mk is a multiple of LCM mn. So mk is a multiple of LCM mn. Then what could we say, yeah? mk is a multiple of LCM-mn, then mk, what is LCM-mn? This is
n over
mn over GCD mn, right, by homework 2. So, m times q is equal to mk, and hence n over GCD mn times q is equal to k for some q is n. And hence okay, these are all strictly positive integers, right? So n over GCD mn divides k is equal to the order of g to the m. So the order of g to the m is mn is k is what? What am I saying? The order, yeah. So the order. So k. So the order of g to the m is n over g to the m. Okay? And apologies for the recording, it's of bad quality, but